Okay, I guess we're actually on time. So let's start. Let me remind everyone on how to ask questions. So if you go to Vova and then you follow the link to the invited talk, and then in there you go to the details, then you come to the session QA, and there you can ask questions, and then we can see after the talk, or maybe if it's really important, during the talk, how we can get you online, or I will ask the question for you. Anyhow, I'm super, super, super honored, happy, you can choose your word, that Doina Precup actually accepted our invitation. It's really, really amazing. And let me also give you a little bit of a background why I'm so excited. So I was actually, I mean, next to all her work, I was also watching and attending the iClear debate or panel discussion. Doina was taking part with Leslie Kelbling and Josh Tenenbaum. And I think it's one of these exciting questions, how to get knowledge into all of our AI, right? And if you think about it, there are all these different ideas, and maybe we'll converge at some point. But Doina has made so many nice and interesting contributions there that I'm super excited to hear more about it. Doina is with CFAR, she is with McGill University, she's also with DeepMind. So when we were meeting a little bit ahead of the talk, I was asking how she's managing all that. I guess this is because she found a way to build knowledge into her own reinforcement learning system. So let's see whether we get also some hints and insights into that. But I'm really so grateful that you accepted. Please go ahead. Thank you.
Thank you very much for the invitation. It's really a great pleasure and honor to be speaking to the ECML audience. And I wish we were in person and we could do this live, but we do our best like it is. I will talk about building knowledge for AI agents with reinforcement learning. So I'll just start by sort of giving the intuition of reinforcement learning if there are any people who don't know what this is. Reinforcement learning is really a setup that's inspired by the way that animals and people learn by interacting with an environment and receiving feedback from that environment in the form of numerical rewards. And so you can see in one picture a little biological agent, a little mouse that's learning how to press a sequence of levers by receiving food rewards, food pellets. And so the setup for our artificial agents is similar. We have an agent that's in an environment. It receives some signals which represent its perception. It can take actions and it receives a numerical reward signal. And its goal is to maximize the long-term return. So that is a cumulative measure of the rewards. But we do this by trial and error. So the agent is never really told what's the right action to do in a particular situation. It needs to try actions out and observe their outcomes. So this has led to quite a bit of success. One of these successful applications is AlphaGo, developed at DeepMind actually before I joined DeepMind. And in this case, we have a system that learns how to play the game of Go, which is quite a complex game, by looking at the state of the board, choosing actions among the legal moves, and just receiving a reward at the end of the game that says whether the game was won or lost. And interestingly enough, even though the agent is not told what are the right actions, but just plays games against itself, it can learn to become a grandmaster at this game and can invent new ways of playing that seem superior to the way that people do things. So that has actually galvanized a lot of interest on reinforcement learning and this combination of reinforcement learning with deep neural networks as a function approximator to represent the knowledge of the agent. Now, one of the goals that motivates my own research is general AI. I would like to have AI agents that have a lot of capabilities in an environment. And while Go is a very complex and interesting game, it is in some sense a very special kind of sanitized task where the agent can fully observe the state, and a lot of the complexities of the real world are not present. And so I like to think of tasks as cooking, for example, where you have an agent that needs to deal with last minute situations. Something is burning, you have to remove it from the stove. It needs to plan ahead in order to make sure that it has the right ingredients available, but also needs to carry out some low-level mechanical actions like stirring and whipping and pouring and stuff like that. And it needs to learn efficiently how to do this based on its stream of observations and actions, and it needs to act in real time. So that's quite an interesting task. It's not what we think of when we think of intelligence, because we all are able to do these tasks quite well, but our artificial agents actually still have a lot of trouble in this kind of context. So what I want to talk about today is some ways in which reinforcement learning ideas can be used to make some steps towards this kind of general AI setup. And in order to discuss that, I'm going to take sort of a little bit more of a peek inside AlphaGo and see what kind of knowledge does an agent like this, which is a pure reinforcement learning agent, have, and how can we leverage that in a more complex general AI agent. Well, if we sort of look inside AlphaGo's head, so to speak, there are actually two networks that this agent has. One of them is a policy network. And so this is a neural network that looks at the state of the board and decides where to put probability on different actions. So in other words, where to place the next piece here. And so one way to think about this is a form of procedural knowledge. What should I do in the current situation? And then there's an accompanying network here called the value network, which looks at the state of the board and estimates the expected return that the agent should have. In this case, that's equivalent to the probability of a win or a loss at the end of the game. So this is a kind of predictive knowledge. It's knowledge about what will happen in the future, and that future could actually take many different lengths. And certainly this outcome is going to be delayed, okay? And so these are two different kinds of knowledge: procedural knowledge, how to do things, and predictive knowledge about the world that an agent should have in order to carry out intelligent decisions. And so we're going to talk about building knowledge with reinforcement learning of these two different types: procedural knowledge, which means skills or goal-driven behavior, and predictive knowledge, which you could loosely think of as equivalent to predicting the effects of actions or something like laws of physics, although the kinds of things that we're going to talk about are simpler than that. And there are three goals to keep in mind. One is that we would like this knowledge to be expressive, so to be able to represent many things, including possibly complex stuff like objects and space and so on. We would like the knowledge to be learnable from data that the agent receives without needing supervision. And that's very important because we can't always have a person looking over the shoulder of the agent to provide feedback. And we would like the knowledge to be composable, which means we can reuse it, quickly put it together if the agent's task changes or if the agent is faced with some unforeseen circumstances. So I will start by talking about procedural knowledge. One way to express procedural knowledge is through the framework of options. You can think of options essentially as controllers or sub-policies that the agent has access to. And in colloquial terms, one way to think about it is the agent needs to have some skills that help it act in the world. So more formally speaking, an option has three components. There's an initiation set, which is a subset of the states where the option applies, or the precondition in sort of more classical planning terms. There's an internal policy that specifies how actions should be chosen while the option is executing. And then there's a termination condition, which is stochastic and tells us the probability of terminating the option upon entering a given state. And so part of this framework has been inspired by macro actions in classical planning, by behaviors in robotics, and by hybrid planning and control setups in sort of automation. Now, how do we think about options in the context of reinforcement learning? Well, in usual reinforcement learning, the agent interacts with the environment in discrete time steps. And so you have a Markov decision process, which is this curve depicted on top. And at every time step, the agent gets to observe something about the environment and then gets to take an action. That action takes one time step, let's say a second or a millisecond. And then we transition to a new state. So we have another one of these small dots here, and the agent can make an action choice there. Options allow for a semi-Markov decision process. So what does this mean? The agent has a decision point. This is the empty circle over here. It can choose an option, and then that option takes control and executes for some period of time. And there's going to be a transition to a next decision point, and now the Markovian property is both in terms of the probability distribution of this next decision point and the time duration that will elapse in between these two decision points. And so once we have options, we can overlay them on top of a Markov decision process. We obtain a semi-Markov decision process. And the interesting thing is that we can use all the different learning and planning algorithms that are available in Markov decision processes at the option level. And so we don't need to invent any new algorithms. And essentially methods like value iteration and temporal difference learning, Monte Carlo, policy gradient can all be adapted immediately to work with options. While options have been typically used as policies, it's actually interesting to think about an extension where you can consider an option to be a full behavioral program. So what does this mean? It means that internally during option execution, the agent can keep track of certain internal variables, for example, the time that has elapsed since the option has been initiated, and the instructions are equivalent to taking actions. And also we can have options invoke other options. So again, while in practical applications, this capability hasn't been used very much, in principle, one could build multiple layers of options on top of each other and use them as subroutines. The other interesting aspect of considering options as behavioral programs is that we can consider various ways of executing. So rather than always using call and return, for example, we can consider interrupts, where if a better alternative becomes available, the current option can be interrupted and cede control to another option through a new decision point. So that's sort of a special form of concurrency. And in prior work, we have shown that this actually always leads to better policies if the agent already has some amount of experience in the environment. Now, programs have syntax and they have semantics. And so options also have semantics. The semantics for them are provided by models. This is similar to primitive action models in usual Markov decision processes. So models for primitive actions consist of an immediate reward and the transition probability to the next state. Models for options consist of a cumulative reward until the option terminates and the joint sort of transition and time distribution at the terminal point of the option. And so oftentimes we sort of collapse these together. And this essentially, the transition model is a discounted probability for transitioning to the next state. Now, models are interesting because they do provide predictions about the future. Specifically, they provide predictions about the trajectory that will happen until the option terminates, and then a special prediction about the terminal point. And many people have shown that having models in addition to options provides benefits beyond just having the hierarchical behavior itself. And so this is an example from the work of Matt Botvinnik. This was a little experiment where you have an agent living in this little grid world here. The agent can move around, but it can also be provided with some options that take it to the hallways. And the agent needs to navigate to a particular goal state. In this case, it's marked by this green square. And so we can consider what happens if this agent learns using just primitive actions. So starts by knowing nothing in the environment, just has to move around randomly using primitive actions until it hits the goal. And then it can propagate the goal information to all other states. And this is the purple curve here. This curve shows steps to the goal. And so learning means that we reduce the number of steps that the agent is taking to reach the goal. And you can see that the agent is somewhat successful in learning this. if we provide options, one advantage is that the agent can move more easily around the environment, because instead of sort of dithering in a corner, it can take a big jump to a particular hallway. And so this is the orange curve here, where the agent has access to options and uses these options to generate behavior. And you can see that the learning is faster. But then in addition, we can also provide models that tell us what are the outcomes of these options. And we can use the model to propagate this information about the goal. So essentially to do planning in a value iteration style and propagate the information about the goal across the environment. And so then we obtain this blue curve over here. And you can see that in this case, the learning is faster, and also the solution that is obtained is better in this case in a finite amount of time. And that is partly because the agent has this form of information that allows it to more effectively take the reward, which in this case is a sparse reward, and attribute it to large portions of the environment quickly. So we're using the models to provide better temporal credit assignment. Now, one interesting question that always comes up is, how should the options be created? Now, a lot of the time in practical applications, maybe somebody knows something about this. You have a robotics engineer that, let's say, crafts some controllers for a robot. But in general, we would like agents to be able to come up with their own set of options and create that from the data as well. And so if we are given sub-goals for the agent to achieve, or some kind of secondary reward structure, like let's say it's good to acquire a key if you're in a game where there's doors, because maybe the key helps you to move, then actually there's a lot of algorithms that already exist that can solve this planning and learning problem. But then, of course, the problem becomes, what's a good set of sub-goals? And so I'm going to talk a little bit about this problem of finding good sub-goals. This is a representation discovery problem that's been studied quite a lot. And there are some sort of strong intuitions that people started with that were then sort of morphed into algorithms that are more sort of based on online learning from data. So one interesting intuition is this intuition of bottleneck states. It's perhaps the most explored idea in option construction. Lots of people have worked on this, including myself and my students. The idea here is that if you have an agent that goes around an environment, there will be some states that allow the agent to circulate between different parts of the environment, and these are interesting states for the agent to reach. There's lots of different ways that you can get at these states, typically by analyzing the graph of transitions that the agent can collect. But this is very much a batch, computationally expensive process where you get a bunch of transitions, you have to construct a graph, then maybe you look at the spectral properties of that graph to identify these interesting points. And so one of the things that I've been trying to do over the last 5 years or so is to come up with cheaper ways of obtaining this kind of structure. And of course, the cheapest thing and sort of simplest thing that you can possibly do is to posit random sub-goals. And so this is an illustration of what happens if we construct options for random sub-goals. In this picture, you have these little ellipses. Think of these as lily pads, okay? And there's a sub-goal at the center of each of these ellipses, and the agent has a policy to move to the center whenever it's inside of one of these ellipses. And so now, instead of thinking of the agent as planning at the low-level primitive actions, the agent can actually consider moving from lily pad to lily pad, jumping across here, and making it to the goal that way. And so here we have a simple navigation task where actually the agent has a continuous native primitive space, but putting in the options introduces a discrete abstraction on top of that. And we've generated these randomly, so you can see they're not particularly good. But still, having this kind of procedural knowledge allows the agent to quickly chart a path in this environment, even after very little data, whereas an agent that's just using the primitive action space after the same amount of data is still stuck in its corner. And so intuitively, this is because in terms of the exploration process, these options allow the agent to move consistently in one direction. There's actually been also some theoretical work by Alessandro Lazarich and colleagues that formalizes the intuition of this example. A more targeted approach is actually to try and learn options that optimize for a specific objective. And so in this case, one can think of the return, the usual reinforcement learning objective, and try to construct an algorithm that optimizes for this. And we have proposed actually an approach for doing this called option critic. This is work in collaboration with my former student, now Professor Pierre-Luc Bacon, and Jean Harp. And the idea here was that we wanted to learn options in a continual manner, in a way that works with both discrete and continuous environments, and while also providing improvement even within one task, so not just in the transfer setup. So the original actor critic architecture is a very famous reinforcement learning approach depicted in this figure. The way we think about it is there's an actor or a policy, and then there's a value function or a critic. And the actor is the one that emits actions and receives state information from the environment. The value function is watching what is happening and is providing gradients for the policy. So it's telling the policy what's the right direction in which to move the parameters in order to improve the total observed return. So actor critic is interesting because it's a continual learning framework. This is all incremental and can be done online and handles both discrete and continuous environments. And so we proposed an extension to this called the option critic architecture, where the policy box has quite a bit more structure, and the value function box also has more structure, because now our agent is going to build a set of options and have a behavior policy on top that chooses among these options. So in the picture, we have these omegas, these denote options. These are chosen by the behavior policy, and each of them has an internal policy and a termination condition. And the way we think about this is the behavior policy chooses an option, that option executes until it terminates, and then some other option gets picked. And during this time, the critic is watching all of these parameters of internal policies, terminations, and the policy over options, and will provide gradients that give improvements to these parameters. And so there are various ways in which we can look at the benefits of such an approach. One of them is to consider a transfer learning problem. So in transfer learning, we have an agent that is faced with tasks that change over time. And so in this case, we can consider our little navigation environment where the agent starts by going to one particular hallway marked in red, and then the goal moves randomly to another position in this room. And we can observe what happens with option critic, and then with some agents that use only primitive actions, in this case, actor critic, which is the sort of the equivalent algorithm we talked about, but in primitive space, and SARSA, which is a value-based algorithm. And so again, here we're looking at the number of steps that the agent takes. So low is good, and you can see that all of these algorithms actually learn pretty quickly how to achieve the goal. Whenever the goal moves, you see this big spike. This means that now the agents are lost. They've lost where the goal state is. But now when they start learning again, the agents that rely on primitive actions take much longer to become good at the new task. And this is partly because they have to re-explore the environment and rediscover the goal. Whereas the option-based agents actually converge quite quickly. And this is partly because they already have knowledge that they've acquired about how to move in this environment, and that knowledge can be leveraged to do fast exploration. The other thing that you observe here is that, having more options helps, but only up to a point. And so if we have too many options, actually it doesn't make much of a difference. We've also benchmarked this quantitatively and qualitatively in several Atari games. And so at the time, BQN was the gold standard. So we compared against BQN, and these straight red lines in the graphs show you that performance. The green curves are option critic. And on the x-axis, we have number of steps that the agent takes, which is equivalent to what was used in the DQN paper. And so one of the very exciting things to me when I first saw these graphs is that the agent is able to achieve good performance and sometimes better performance than DQN within the same experience budget, even though here we don't have transfer learning. So that's an interesting aspect because a lot of the time we build knowledge because we're going to use it later in some other circumstances. And so we can afford to spend the time to do that. Here we have to solve these tasks at the same time, and there is no other task that comes afterwards, and yet still building this knowledge is proving useful. The bottom graph shows a qualitative result from a game called Sequest, where you have this little submarine that has to rescue a diver. And in this case, we're learning two options that are marked here in the bar by white segments and black segments. And so we can see two interesting things here. One is that these options are taken for quite a bit of time. The other thing that we can see is we can sort of zoom in and probe what these options are doing, and you discover that they actually do things like going all the way to the top of the water because you need some air, and then going down to rescue the diver. So that's a nice sort of semantic interpretation for these games. One of the problems is that this procedural knowledge might disappear over time. And so we observe this when we run option critic because, in the end, in a single task, using primitive actions is just best. And so if we want to keep the options around, we kind of need to use regularization in order to encourage them to preserve their length. And the notion that we use is actually inspired by this framework called bounded rationality that is often used in cognitive science and psychology to describe reasoning about choices in animals. And the intuition is that reasoning about action choices is actually expensive because you have to think, there is energy consumption that's involved there. But also because if you're thinking for too long, the prey runs away or, something else happens. So there's a missed opportunity cost during that time. And so we model this in option critic essentially by penalizing the agent for making choices. So every time that the agent wants to switch options, it can do so, but it incurs a small cost. And in fact, you can show that this is similar to saying the advantage of the new option that's being chosen has to exceed a certain threshold for switching to be allowed. And so these are some results, again, from Atari games, where we are looking at options with no regularization. These are the curves depicted in yellow, and then various amounts of this deliberation cost regularization. And what you can show is that the deliberation cost does achieve the goal of the agent preserving the length of the options. This is in sort of these log termination graphs where you can see an agent without regularization terminating all the time, and more regularization allows the agent to terminate more rarely. That sometimes helps and sometimes doesn't help, and that's what we would expect to see. Because sometimes if you commit to an option, maybe you stay stuck in it for a long time. But generally speaking, if we believe this knowledge to be important in the lifetime of the agent, then it should be preserved. And this is just another little illustration of this idea in a game called Amadar. And so here we have an agent that uses just option critic on one side. And you can see that there's options, but the agent ends up sort of switching them very, very quickly, and you get these very little segments of experience. The middle graph shows options that arise from using deliberation cost. You can see that the agent is taking the same option for quite a while. And the last graph shows where these options choose to terminate when we're using deliberation cost. And interestingly, we get termination around the hallways, which are places where the agent can make a choice to switch the direction in which it's going. And then there's some segments up top where there's sometimes an enemy that comes and attacks, and so the agent has to terminate because it has to switch direction over there. So one thing that I would like to point out is in this case, we are learning some termination conditions that are essentially giving us some bottleneck states as a side effect, even though that was not explicitly stated. And so some of these heuristics that people have introduced initially as prior knowledge in option construction can be obtained just by using gradients. Another interesting question that arises is, should all the option components actually optimize the same thing? So an option critic normally will optimize for return, but actually the deliberation cost, one way to think about it is it's a special cost that gets added only at termination. And so it's an objective that the termination condition has to pay attention to, but not the internal policy of the option. So in some more recent work with colleagues at DeepMind, we have sort of generalized this idea by introducing a variation of option critic called termination critic, which allows the optimization criterion for the termination condition of an option to be independent of the optimization criterion for the policy inside the option. And so in this case, for example, we can make the option terminations focus on predictability, so finding things like bottleneck states, and we can let the policy inside the option focus on optimizing reward. And so we've instantiated this in a series of experiments that you can see here. A2OC are the usual option critic results. And so what we see here is depending on the deliberation cost, the options either terminate all the time or still terminate quite a lot. Whereas if we're using the sort of general result and we ask the agent to minimize the entropy at the final state of its options, we obtain options that are more focused and terminate in very particular areas of state space. And in terms of number of steps to go, this has a positive impact as well. Now, of course, deciding on minimizing entropy in some sense is also a heuristic. And in principle, one can plug in other kinds of terminal reward functions there. So I've talked about procedural knowledge. Now I want to talk a little bit about predictive knowledge for reinforcement learning agents and how to build this. And so to talk about this, we are going to focus on the kind of predictive knowledge that almost all reinforcement learning agents use, which is the value function. Okay. So the value functions is very much a textbook definition, a la Sutton and Bartow textbook. Here we are looking at an agent that is in an environment. It receives a reward function. This reward is a function of state action pairs. And there's a discount factor, which is between 0 and 1. And it tells us essentially what's the probability of the agent's trajectory continuing at every time step, right? So the agent lives to see another time step and another reward. And we typically condition this on a policy, an internal policy that the agent is using. So one way to think about this formula is we have a signal of interest for which we want to make a prediction. This is the reward in this case. And we have a time scale over which we want to make the prediction, which is implicitly defined by gamma. And in this case, gamma is fixed. It's always the same. And depending on gamma, one can basically compute the effective horizon over which the agent will care about the reward. Because if this gamma product becomes too small, then essentially everything afterwards is close enough to zero that it becomes negligible. And of course, we can also have an optimal value function. The optimal value function is optimizing over the space of policies given a certain reward and given a discount. So value functions are forms of predictive knowledge about a very specific signal, which is the reward, and using a specific way of expressing the timescale. The nice thing about them is that they allow us computationally to build interesting algorithms like temporal difference learning, for example, because they allow us to do bootstrapping and sampling. And this is really based on unpacking these expected value equations. Sampling essentially allows us to sample this expectation in order to estimate it. And bootstrapping allows us to use Markovian structure in the environment to open up this expectation into different terms and approximate some of these terms using our current estimate of the value function. And that's sort of the crucial idea in Q-learning and TD and other algorithms like that. So we have a lot of interesting algorithms for learning value functions, but people say, oh, value functions are restricted because you have only one reward and you're only learning how to predict that reward. And in general, we would like our agents to make many predictions about many different things, many different ways of behaving at many different timescales. And this is just an illustration of that taken from Adam White's thesis, who played a very important role early on in defining these concepts. This is data taken from a robot that Adam was working with, and it's conditioned on policies. There's different policies here in the different rows, and there's different sensors, and these sensors are being predicted at different timescales. You can see that there's a wealth of information in this data than that one may want to model, and we're going to try and use reinforcement learning tools for that. And so this is the idea of generalized or general value functions, also called GVFs. We are going to use something like a value function, but generalize the content inside of it in order to make it more interesting from a knowledge point of view. So we have here a cumulant. This is like a reward, but it doesn't have to be a single number. It could be a vector, it could be a matrix. And then we have a time scale over which we want to make these predictions. And now we're going to allow this time scale to depend on state. And so in other words, we can decide, for example, that we are going to have a gamma discount of 1 all the way until some terminal condition is met. Then we can set this to 0. And so this results in now value functions that are conditioned on 3 different things: the policy, like before, so the way of behaving, as well as a cumulant and a continuation function. And there are some special cases of this. For example, universal value function approximation, work by Tom Scholl and colleagues, is a special case where we fix cumulant and continuation function gamma, and then we optimize for them. So we obtain a V star, an optimal value function with respect to this cumulant. And then they propose a particular neural network architecture where, in fact, we can make predictions for all of the possible cumulants in an environment. It's an environment where cumulants are essentially equivalent to goals. So now we can have an agent that learns about many different aspects of its environment and at many different time scales. And we're going to use off-policy learning ideas in order to allow the agent to examine its data and do all this learning from the data. And so one way we can think about this is that we are going to have these predictive pieces of knowledge, these general value functions that take inputs, not just the state of the agent, but also this other information, perhaps embeddings of the cumulant and the continuation function and embedding of the policy, and can provide an estimate of the value function. And you can notice that these are like building blocks. Then we can now hook up to each other in various ways. So for example, we could take, in principle, a cumulant from a general value function and provide it as an input to another general value function that just works at a different time scale, or we can do the same thing with the state. And, you know, if this looks like a very sort of general framework, it's because it is. There's actually different ways to show that existing concepts become special cases of these general value functions. So one interesting concept to look at is that of successor features or successor states. Successor states have been provided as an idea by Peter Dayan back in the 1990s. And the idea is to represent a reinforcement learning agent state, not through its local perception, but through a description of the futures that can happen from there. And it's been shown to have some interesting parallels, for example, in the hippocampus in biological agents and the way that agents think about trajectories in the hippocampus. Successor features is just a generalization of this idea to use feature vectors. And so in GVF terms, the way we think about this is we're going to have a cumulant that is just the agent's feature vector. We can fix its policy, and we can provide a discount. And now we're going to have a value function that can estimate the future distribution over trajectories of the agent. And there's an interesting property here that basically says that if we consider a set of cumulants and the policy, any linear combination of those cumulants, W transpose C, leads us or can be estimated by taking a linear combination of the value functions for these individual cumulants. Okay. This is very much relying on sort of linearity properties, but if we unpack this a little bit, what it means is that we could estimate some pieces of knowledge, value of a particular policy for different cumulants, for a set of cumulants, and then we can single shot estimate the value function of any particular combination of those cumulants. So that is now starting to get into this realm of being able to combine the existing knowledge in a very efficient way without relying on new data at all in order to produce a solution to a new problem. And we're going to talk about this a bit more in a bit. Another kind of thing that can be expressed as a GVF is a model. And so this is an example from option models. I'm taking here the reward model for an option where we take rewards and then we accumulate them during the trajectory of this option. And so one way we can think about this is that the signal of interest is the reward, marked in red here, and we're going to accumulate this over the time scale of the option, and that time scale is defined both by the environment through its discount factor gamma, as well as through the desire of this option to continue, which is this 1 minus beta here. And we can do this for the reward model, but also for the transition model of the option, for the value functions over options, and so on. And that's kind of interesting because it shows you that these expectation models, in fact, can be thought of as value functions. And so all of the mechanisms for learning value functions will apply here. Obviously, this doesn't give us a full generative model, right? It gives us an expectation model, but that estimation process can be very effective if we accept this limitation. There's lots of different other approaches that we can express as GVFs, but instead of telling you about that, I just want to show you an interesting way of leveraging GVFs in order to synthesize new behaviors. And this is an idea that we published in last year's NeurIPS, work, and again led by Andre Barreto, but based on some intuitions expressed in an earlier talk by Rich Sutton. And so the idea here is to think about a generalization of this notion that we can estimate some general value functions for some particular behaviors and then quickly combine them to obtain a solution to a new task. And so if you imagine an agent that's learning to play piano, okay, and imagine that this agent learns how to press individual keys. Okay, so think of each key as being a cumulant, and this agent can press the keys one at a time. Okay, we would like to have this agent then be able to play chords. So a chord now is a weighting of these keys. Some keys will be louder, some keys will be softer, some keys may not be pressed at all. And we would like this agent to be able to figure out the behavior for making chords without necessarily learning again how to press with each finger, right? Each finger now knows what to do. Each finger knows how to press a key. We just need to put this together to make a chord. And so there's a very general box here, generalized policy evaluation plus generalized policy improvement, that lets us take the framework of GVFs and combine them to produce an integrated policy. And so just to give you a sense of what this can do, we have here an agent that is in a little arena. This is a little quadruped robot simulated. And we can train this agent to go to some particular goal positions. And so in this case, we're going to pre-train the agent with 3 given options, red, blue, and green, to go in a goal position in each of these areas. But then we can ask the agent to satisfy simultaneously multiple goals. And so, for example, we can tell the agent we would like you to go in between the vertical direction and the 120-degree direction. Or we can tell the agent, we just want you to go away from the vertical direction. So give a negative weighting to that direction. And so then we can take generalized policy evaluation and policy improvement and have the agent synthesize a behavior to go in any of these yellow marked directions that are around here. And so the picture here is showing us now returns. And of course, here we need to do some pre-training. So this grayed area here is denoting the amount of time that we're going to spend to pre-train the individual options of the individual policies that we have ahead of time and their associated value functions. But once we have that, we can have these agents that play chords. And we can compare this against agents that just use flat learning. So this is the red curve here, DPG, which is a sort of good algorithm in a flat sense for this case. And we can also sort of compare what happens here compared to an agent that is using the options in a call and return fashion. So doesn't know about the GVFs, doesn't do generalized policy evaluation and improvements, just sort of learns how to combine the options. And this agent also does very well at the beginning, learns very quickly, but then it levels off. And this is because in this case, the agent is bound by the options that it has to choose from that set. Whereas doing generalized policy evaluation and improvement allows the agent to access a much larger space of policies. So there's one other thing that we need to talk about that we've mentioned very briefly at the beginning, but we haven't really delved into, and this is the issue of initiation sets. So initiation sets or preconditions tell us what is possible to do in certain situations, and biological systems actually are really good at understanding this. So here there's a cartoon picture of a person which is in the state that there's a tree nearby, and so therefore understands that there's different possible uses for this tree. One of them might be more entertaining, like hanging from a branch, or the tree can provide shelter from the rain, or the tree can provide shelter from an attacking animal, and so on. So Gibson in the 60s talked about this ability of animals and people to understand what is possible in their current situation and to leverage the objects that are available. And he coined the term affordances to refer to this relationship between what is in the environment and the ability to carry out certain actions sort of successfully. And so one way to think about initiation sets is that they tell us which options are possible, which options might have a chance of succeeding given a particular state. But we haven't really done very much with that so far, besides sort of introducing the notion, partly because of the difficulty of learning this. And so in recent work with Kimia Ketterpal and colleagues at DeepMind, we have looked at formalizing this idea. This is a recent paper that we published in ICML. And so how should a reinforcement learning agent think about what is possible in its environment? Well, one way to think about this problem is to consider, again, this little navigation task where the agent can move in different directions. And so if you ask this agent, where, if you were to go left in this environment, where would you end up? There are some states that are achievable here, okay? These sort of gray states, and the states with X's in them are not achievable. So now we're going to think of an intent as what is the agent trying to do? If the agent is trying to go left, then the intent is, one way to think about it is the agent wants to move into one of these states that is in the gray area. And we might have a probability distribution over these states. Now, what's the affordance? The affordance tells the agent from which states with which actions this is possible. And so in this particular case, there are some states in which the action left allows the agent to actually move, change its position, and in other states this is not possible. And so we can define an affordance as a relation between states and actions. And here, for example, you see what's the affordance of going left. This marks all of the states in which the going left action succeeds in moving the agent to the left. So why is this interesting? Well, we can now think of these affordances as, in some sense, knowledge about some partial models. These are models of the environment that tell us where applying this action is going to lead to something that is close to the intended distribution of states. And we can use it both to limit the agent's choices as well as to sort of improve its model learning capabilities. And so this is the part that I want to show you, where we leverage this notion of affordances to learn partial models. So imagine that you have an agent that needs to learn a dynamics model. So where will an action end up, or where will an option end up? Okay, so this is now a generative model P parameterized by a parameter vector phi. Usually we do this by maximum likelihood. We take an agent, it's going around the environment, we take state action next state pairs, and we fit a model. The problem is that actually in many states, maybe the action fails, and moreover, which states we're seeing with successes or failures may depend on the agent's policy. So while I write here this model as going state action next state, actually the model is going to need to generalize over data that comes from many different parts of the environment, and the input distribution, the distribution of state action pairs, is going to be now stationary because this agent is also doing a task in the environment. With the affordance, we can essentially say, if in certain states an action does not achieve intended consequences, we simply will not consider it. And so instead of using log likelihood to fit this model, we're essentially going to use a masked log likelihood that simply disregards any actions that are not feasible. And so this is just an empirical illustration of where that leads us. This is a model learning task where we're considering Gaussian models. And so on the top, you can see an agent that is trying to figure out the model for a going left and a going right action in a continuous domain here. And we have two different kinds of problems that arise. One of them is that this going right action, which is this purple blob, really intersects walls because the model is a Gaussian and this action is actually not feasible next to a wall. But the model doesn't know that, and it's sort of trying its best to do something here. And the going left action, which is this blue blob, in this particular case, going left is feasible, but still this model is quite a bit off from the true model, which is depicted here in gray, mainly because we are not getting sort of the right stationary data distribution to estimate this model. But if we're using affordances, then actually this pink model will not even be estimated when we are close to a wall. And the blue model has better data and is now much more consistent with the truth. And so the affordances allow us essentially to stabilize the data distribution that is going into learning a model. So I'm going to sort of wind down here. I just want to emphasize that reinforcement learning suggests to us some very powerful tools for knowledge representation, options, general value functions, and affordances. One of the reasons I'm excited about these ideas is that I would really like us to move in the direction of building, integrating lifelong learning AI agents, and have the agents have these capabilities of having options and general value functions internally, combining them as building blocks and using affordances in order to control the data flow and the branching factor in decision making. There is one really important problem that I haven't talked about, which is if we want to build these long life agents, how should we evaluate them empirically? And I'm just going to say this very quickly. I think this is a very important open problem because returns, which is what we normally use in reinforcement learning, are quite simplistic. They only give us a very sort of small dimensional idea of what these agents know. And while qualitative analysis, like some of the things I showed you, is interesting, it's also difficult to draw general conclusions from that. And so we need to devise some new methodology for understanding what these agents are capable of doing. And so one thing that I would like us to do is to move much more to a hypothesis-driven evaluation of these learning systems, where if you have especially an agent that is interacting with an environment for a long time, we should be able to make some hypotheses about what the agent should know or how it should behave in a certain circumstance, and then design specific experiments to test this hypothesis and use the conclusions or what we learn in order to understand how we can improve our agents. So not just returns, but actually hypothesis-driven testing of agents. And of course, ideally, we would be very patient and let the agent go, indeed, for a long time without tinkering with it. So I'll stop there. Thank you for the opportunity to talk, and I'd be happy to take some questions.
Great, thank you. I was just about to finish one question, but let me maybe just stop here. But maybe I start, and then meanwhile, some more people can already ask some more questions in the session QA. So just now, because of this hypothesis-driven evaluation, does that mean that we have to also focus more on the communication? I mean, that you as a human understand what the robot is really doing and vice versa, and particularly also the other way around. And so do you plan to set up the whole framework that you have now also together with some form of symbolic translation or whatever? Or
that's a great question. And I think there's two aspects to this. One is simply perhaps getting more inspiration from psychology, where people do assess, for example, developmental milestones in babies, or they assess what mice or other animals know as a result of training. And that can be done without necessarily having a language like a communication channel. And so I think there are some interesting lessons for us to learn from that literature about how to set up these types of experiments. And some of it may just be mimicking these experiments that are already done in psychology. This being said, I think this question of communication is really interesting, partly because, if you think about abstract knowledge and being able to manipulate concepts and objects, the communication is one drive towards abstraction. And so, in fact, we are also quite interested in, for example, emergent communication among AI agents, because that can really drive these agents and motivate them to create more interesting high-level abstractions.
yeah, so I think that's also where I was coming from. I mean, given that Peter Dayan is now in Germany, we were talking a little bit, and then there are also people in Darmstadt working on applying ComDPs to explain human behavior, and that was one of my questions there. But let me maybe first read another question. I still hope that there will be some more. So here's one question. Is it possible to think of hierarchies of options? If options are grouped sequences of actions, could we try to learn collections of options in a tree-like format to learn higher abstractions?
Yes, so in principle, we can have multi-layered hierarchies of options. And so options can call other options and we can build as many layers as we want. Interestingly, in empirical experiments, we have never really been able to show clear benefits of having many layers. And so it's not clear if this is because the tasks that we're looking at are still quite simple and in some sense can be solved with sort of 2 layers of abstraction, you know, a primitive layer and an option layer on top. But in principle, one can build multiple layers, yes.
Okay, let me just try. Okay, he seems not to be around anymore. Okay, so then there are some other questions, maybe some of mine. I have lost a little bit my overview. So have people tried to make use of options within AlphaGo or AlphaZero? So in a sense, imagine that you now analyze within chess what kind of options are learned and are they meaningful? Are they more meaningful from a computational perspective?
Yeah, that's a really interesting question. So in AlphaZero, which is the planning version, there are internally sequences that are option-like that are used in the planning process. Now, these are, unlike sort of closed-loop options, which is what I typically work with, these are open-loop sequences. So they fit in the options framework, but they're not the kind of thing that we have explored a lot in the options framework. And it's a very interesting question to think about sort of what's the role of open loop versus closed loop in that situation, especially in planning. So one intuition is that having open loop options is useful when you are doing things at the beginning. So what you want is just sort of exploration and your value estimates are not very good. Whereas closed loop options might be better when your value estimates are becoming good. And so making, you know, leveraging those estimates in the internal policy becomes more important.
And here's another one. In lifelong learning, shall we put a limit to the growth of options or models?
So in principle, if you have more and more options, you have an additional computational burden because now you have choices that you have to make. The branching factor increases. And so the work on affordances is really, part of it is motivated by this need to keep the branching factor in check and provide some search control. You know, the other question is, do you have a very large library of which, for example, a very small set is under consideration at any given time, and a small set is actually also updated from the current stream of data. So even if you allowed this, this overall library of knowledge to grow, if you have a good mechanism for focusing attention on a small subset of it at a time, that would be a perfectly good answer. How to do that, I think, is also very much an open question.
Well, and then additionally, there might be this interplay with the rationality principle, right? That you don't want to have too complex programs and too complex knowledge, because then you are lost in thinking and,
Exactly.
and you can't take actions anymore. I mean, so generally there is the other session starting, but I guess people who want to join there can go. I still have at least one question I really would love to understand. So I got a lot excited when I heard now about the affordances and the way you interpret that. And I was wondering, somehow it reminds me of the early work on bisimulations by Bob Given and so on, maybe in a more local fashion. And then meanwhile, there was some more work on understanding it more from a symmetry perspective. And I think now recently there's all this work on equivariant learning and deep learning.
Yes.
And so I was wondering, can we make a connection and say, okay, even the predictive states, whether we use states or feature representation, isn't that all a form of getting something like equivariant learning? Because I think that's the generalization even of the other stuff running. I mean, of course, they have the problem that they also don't know where the symmetries are coming from. So don't get me wrong. But yeah, somehow I saw a connection. I'm not sure. I mean, whether it's true.
I think you are absolutely right that there is a connection to equivariant learning. And so in terms of bisimulation, I think of bisimulation as a very sort of extreme example of this particular approach, right? Where state action pairs really all have exactly the same effect. And there's actually a notion that we explored at some point with Prakash Panangadan and a couple of students, which is called lax bisimulation. So where you can do something like bisimulation, but over state action pairs. Mm-hmm. And so now symmetries become much easier to represent. And what we did in this paper, actually, I didn't get into the math details of it, but essentially we have approximate models, which is more like an approximate notion of bisimulation. Now, the stuff that we do here, one way to think about it is we're focused only on the transition and nothing else. And the bisimulation work, also the Bob Given work, the rewards are also taken into account. And so actions are considered equivalent if they have the same rewards and the same transition distributions. Whereas here we're really focusing just on the transition distribution and putting a criterion on that. But I think there's quite a bit of potential connection to the newer work on equivariant learning. And it would be nice to understand that. Perhaps one way to view the affordance work is that we're trying to do equivariant reinforcement learning.
Yeah. And then maybe with a very simple, by making use of a neural network for the affordance model. I mean, it's a hack for now. And of course, then one should develop a full, more formal approach. But somehow I feel like that there's a lot of value in there. So we did recently, it's submitted now, an experiment where we used DQN, but instead of having fixed activation functions, they are learnable.
Ah, cool.
And it's funny, just because they are learnable, we are beating all the standard DQN. You get something like, I don't know, 300%, 3000% improvements in score.
That is really interesting.
I just feel like there's still so much room in improvement by making the deep nets or the function approximations more flexible, but then at some point also providing some form of making use of symmetries. It's a gut feeling. It's really, I did only a little bit reinforcement learning, and we want to do more now again. It's so fun to work there. So that's why I was also so excited. But yeah,
agreed.
Would be great to do something there. Okay, I don't see next to some of my questions any other questions. I guess we can also stop here because there's some booths going on, so maybe people want to go there. Doina, thank you very, very much. I will definitely send you some emails about what we just discussed. That sounds super, super interesting. And maybe we can also think about this connection to Konstantin Rukov and Peter Dayan and so on, and see how this human stuff can also help us a lot. Thank you again.
That would be wonderful. Thank you very much. Thank you.